Okay, well, I'd just like to thank John Williamson and Peter Rowlands for letting me talk at this this conference. As you can see from the title, at least this talk is partly about a very old problem that goes back in the Western tradition, at least to around 500 BC to Zeno's era, and so the paradoxes in time and motion that has been with us for a long time, they're very general, and they appear in different ways in philosophy and mathematics and physics. And the talk is basically going to be more specific than these paradoxes. The talk is really about what I think is, in a sense, something that's been missed in the history of physics, and what's been missed, I think, is that well, when special relativity was discovered, the physicist concept of time was changed completely. Now, shortly after that, quantum mechanics was discovered, but Minkowski space and special relativity was still a bit new, and the transition from old quantum theory to modern quantum theory really happened. Well, it of course happened in the absence of the Dirac equation, and in a sense, what settled into the physics community was that quantum mechanics became, in a sense, an overlay to either classical mechanics or relativistic mechanics. And so that is now prevalent in both pedagogy and in research. And the alternative that is that well, perhaps quantum mechanics is in actual fact a result of special relativity is not often considered. So really the objective of this talk is really to point out that relativistic time dilation by itself is sufficient to really require us to reconsider what we mean by the world line of a particle, and it turns out that if we do that reconsideration and we start in the discrete world, we get more than one alternative. One alternative is just end up in Minkowski space, but it turns out there is another alternative which takes us directly to the Dirac equation. And the most pleasing aspect of that is when you go through that argument, you actually find out things that you don't see when you're just confronted by the partial differential equation itself. For example, you see why you see what wave functions actually do, and you see why they are in a sense ghostly images of probability density functions, and why there is an association between something that you think of as being intrinsically local, like a particle, and something that's non-local, like a wave. So my objective really is to do that, and so here is really the talk structure. But I guess I should just mention, when I started writing the talk, when I introduced time dilation, what happened was he took over completely, and by the time I caught up with him, the length of the talk had stretched from 1 hour to 2. So we made an agreement that I would get the first hour, and if I was allowed back here, he would get the second hour. So we won't really come across time dilation until number 3 down here. So here's where we're going to get to. And we're going to start with a prologue, and the prologue is really there because the problem is quite general, and although we have a specific target, we need to in a sense, figure out a way of getting there in such a way that we don't get lost on the way. So the prologue is a little bit long and general, but once we finish with that, we start with probability, because probability is a theory, really, that I think we can all agree is pretty stable, and we can follow what happens. And so we're going to take the idea of binary choice and go from very, very simple mathematics, and remarkably quickly we're going to discover some classical equations, the diffusion equation and the telegraph equations. These are all quite well understood, and from the point of view of, for example, kinetic theory, but also from probability theory. The surprise, and really the only surprise in this talk, is that what we also do is we find the Dirac equation. And when we find the Dirac equation, it's only a very minor heresy, because we understand it completely from the point of view of probability theory, which is something we understand and trust. And it doesn't annoy the physicists, because by finding it in the way we do, we see, oh, it's completely not the context in which the Dirac equation is used by theoretical physicists. So there's no real controversy, but it's just an interesting thing that we find the Dirac equation there. So if I'm allowed that for a second talk, we will then go through the entire argument again, and from the point of view of time dilation, and see that in actual fact the probabilistic argument breaks, and then it becomes actually a lot more fun, and you get a much better picture of the Dirac equation in its usual context. So I'm going to start this talk doing something that one shouldn't do, which is to, in a sense, come up with stereotypes and caricatures of what the various people concerned with this do. There's a reason for doing this. The reason is simply that when we plot our path towards the equations, the classical equations that we know and understand, and eventually towards the Dirac equation, we want to know exactly where we are. So these are stereotypes of what mathematicians, applied mathematicians, and theoretical physicists do, and we're just using them so that in the end we're going to have perspectives from the different fields about what's going on. So the stereotype of the mathematician is simply that it's really all about grammar. It's about following the rules for symbol manipulation, and at the end, mathematicians tend to think, well, contact with the real world is superfluous and sometimes simply misleading. So we're not going to go there. We're going to stay with the mathematics, and that's that. Now, the job description of an applied mathematician is quite different. So here, an applied mathematician, what he or she does is he looks for some physical argument suggesting that the math encodes some understanding of whatever the process is that he or she is looking at. And that's, in a sense, it's a recursive process, and it's important that you come into the problem with having some idea of what's going on in the physical process, and you're in the end you look at the math and you look at the physical process and say, well, look, does the math actually encode my understanding of what's going on? So what happens at that point is, if the agreement is really good, then you say, well, okay, the mathematics provides a model or a theory of how things works. Okay, so now we come to theoretical physics. Well, so the claim here is that prior to roughly these dates, theoretical physicists really were applied mathematicians, but they were focused on the things, the systems that physicists were interested in. Those dates are simply roughly the dates of Maxwell's equations and quantum mechanics. When Maxwell's equations came around, the idea behind applied mathematics, as suggested above, became a little bit dicey, and when quantum mechanics arose, it completely fell apart, because quantum mechanics evolved from old quantum theory, which was simply how do we find these discrete numbers? And they occurred as eigenvalues, and so there was a because the mathematical tools available to physicists was really the differential calculus and differential equations. Schrodinger's equation appeared, and the theory sort of evolved from that. So, prior to about that date, applied mathematicians and theoretical physicists did more or less the same thing. But since that time, theoretical physicists, by and large, start within a given theoretical framework, and they work within that framework. And of course, the rather difficult and slightly embarrassing part is they have to interpret the end results of the calculation at the end, and that's tricky. But the whole idea, in a sense, is different from the applied math. So I just also want to point out that associated with this, there are, in a sense, different tensions within mathematics and physics. And in some ways, it's easier to see it in the realm of the mathematician. For mathematics, discrete versus the continuous has always been a problem. So number versus magnitude, and it's really all about infinities. And what we're actually going to do, we're going to borrow a couple of fabulous mathematicians from history, Kronecker and Cantor, who are in the end going to act as arbitrators when we go through our calculations. The analog, I mean, several analogs in physics, but the one we're really interested in is the idea of classical versus quantum calculations. So whereas mathematicians, in a sense, they've always had a struggle going from the discrete to the continuous. Physicists since Newton have lived in the continuum, and so they tend to think more along the lines, when we come to quantum mechanics, of going from the continuous to the discrete. So you can think of the quantum mechanics is really a probability calculus, and a lot of its targets are getting discrete numbers from a continuous description. Whereas mathematicians, the struggle has always been to build continua from the discrete. So that's a bit of a sketch of the two problems side by side, and we're going to bring in two mathematicians to, in a sense, arbitrate our calculations, because the whole thing is perhaps a bit clearer on the side of mathematics. And so here are our two mathematicians, and I'm afraid this is not going to be. This again is a caricature. I mean, they were amazing mathematicians, and all we're going to do is we're going to have them represent a kind of argument. And so the one that Kronecker will stick to, and did stick to throughout his life, was, God created the integers, and all the rest is the work of man. Cantor, who was his student, was equally passionate about the other side of the argument with transfinites. And I mean, it was a little bit sad what actually happened in history was that Cantor respected Kronecker as a mathematician, but Kronecker actually never really, I mean, he thought the whole idea behind his work was seditious. I mean, he just the two can never see eye to eye, and we're going to bring them in as arbitrators, and we're going to, in a sense, sit in the middle as applied mathematicians, which is something that applied mathematicians can do, because the way they work is they say, what is my understanding of this physical process? If it's X, I'm going to look into the vocabulary of mathematics and pull out whatever mathematics I feel reflects that understanding. So the two different perspectives of Kronecker and Cantor, we're going to ask them their opinion on the mathematics that we're going to use as we go through the derivations. Okay, so this is really about what the aim of the talk is. I want to show that in actual fact, a sizable fragment, which is really just a single particle a Dirac equation, can be reclassified as applied mathematics, because we can indeed get at it through probabilistic arguments, although not in this particular talk. So it will turn out that it's sufficient to do that, provided we start with special relativity and we start from a discrete perspective. So this talk today is we're going to always start from the discrete perspective and then work towards the continuum. So what we'll find is that how and when you take the continuum limit determines whether you discover a Minkowski space or the Dirac equation. And the interesting feature of that is, in actual fact, once you've taken the continuum limit, the obvious connection between the classical and quantum is seen to be one way. That is, you lose sight of what the applied mathematician needs, which is some cogent physical argument to get to the equation in the first place. So how will we deal with that? Well, we will always start in the discrete, and we'll see what happens when we take the continuum limit. And we're going to get a hint in this first hour what it is that makes the transition from the classical world to the quantum world difficult, and it turns out to be time dilation. All right, so where are we going to start? We're going to start a place where we trust, right? I mean, the probability model has been around for a long time, and it's, yes, there are paradoxes in probability theory, but compared to the stuff that you run into in theoretical physics, it's minor. So we're going to start. So here's a sort of fairly modern statement of the three axioms. We're after a probability measure, so the domain of that has got to be some event space, and so we have three very simple axioms that we're dealing with. Basically, the measure itself has got to be non-negative. We've got to have the probability of the sample space is 1. So to a physicist, that's just saying you have to normalize the probabilities appropriately. And then the thing that makes probability work is this guy here, that provided that the events are disjoint, then the probability of the union is the sum of the probabilities of the individual event. So assuming everything is disjoint, that's what makes the probability model work. And at this point, we're not really going to argue about the countable infinities here. We will always, in actual fact, start with finite unions and sums, and we'll take the continuum limit explicitly from the discrete to the continuous. Okay, so here are the three axioms, and the idea is that the mathematics relies primarily on counting arguments and enumeration, and that's why it turns out to be so useful. So let's start with something very, very simple. So this is the simplest thing you can start with a probability model. So we're going back to the old heads or tails, right? We're flipping a coin and we're saying, the sample space is this, two symbols, H and T. Here's the event space, okay, where phi is the empty set. And we usually say, well, okay, the probability of heads is a P, where P is some non-negative number between 0 and 1, and the probability of the sample space being 1 means that the tail has to be 1 minus the probability of the head. So we're not allowing the thing to line on its side or anything. It's either heads or tail. And of course, if the coin is fair, then P is a half. And as long as P plus Q is 1, the axioms are satisfied. And so what I want to do now is to link this to counting. So we want to see how it's related to counting. So we're going to shift to the idea of random variables, and we're going to say, okay, we're going to replace the symbols head and tail by 1 and 0. So the head representing, in a sense, something is there, and the 0 meaning it's not there. So you can tie this directly to the idea of counting. So let's look at a counting problem in a way that it's going to be folded into probability. Just ask the simple question, well, how many distinct 4-bit words are there with checksum 3? So we don't have to do any work with this. We can just say, well, okay, we can just, there they are. And we notice that we can enumerate these things and say, well, there's 4 of them. And we can write that in a way, knowing how these things work, is 4 choose 3. And so if the word had n bits, and we were looking for a checksum of k, it would be n choose k. So let's now fold that into a probability problem and say, okay, in a sample of 4-bit words, any bit is 1 with probabilities between 0 and 1, and all bits are independent of their neighbors. So what's the probability that a randomly chosen word has a 3-bit sum? Well, here we go. There they are. Right, we can count them. And each of the ones has probability p, and each 0 has a probability q. Independence gives us the probability. And so notice that the probability that the checksum is 3 consists of 2 things. There's this guy here and that. And so it's a combination of number and magnitude. Okay, so we have a counting problem, and the counting problem is related to magnitude by the fact that the probability of the sample space has to be 1. So right, so now what we want to do is we want to go from heads and tails to instructions, so that we can move over to walks. So let's do that. Well, first of all, let's just construct the probability mass function, which is the function that gives us the information that covers the entire sample space. So we can phrase this whole thing as we're saying we have a sample of 4-bit words. Any bit is 1 with probability p. All bits are independent of their neighbors. What is the probability mass function for the value of the checksum? So we have these boxes. And the thing to notice is that each box can be 0 or 1, and they're independent. So if you walk through those boxes, then there's an instruction set that comes along with that. And so you can go from the 0s and 1s back to the symbols and say, well, okay, let's just have a look at this and take the juxtaposition as multiplication and say, well, let's look at this guy. Well, that's just 1 on the left, but here's the binomial expansion. And from that, we can extract, oh, well, yes, well, here is the probability mass function. And again, same sort of thing. We've got number, this binomial coefficient, and we've got magnitude. So we can figure out the probability mass function. Okay, so now we're going to go from instructions to walks. So we instead of expanding this thing symbolically, which gives rise to 2 to the n sequences that look like heads, tails, and so on. What we want to really do is do a switch and say, okay, heads is going to be replaced by big P, which is going to be taken as persist in the walk, persist in direction, and T is going to change to S for switch. Okay, so at each step in the walk, you either persist in the direction they're going, or you switch. Okay, so the binomial expansion is now an expansion of instructions for a walk. And so let's consider a square xt lattice where at each time step this delta t is some epsilon, and a particle either persists in its current direction with probability p, or it switches with probability q is 1 minus p. So what does this look like? Well, okay, so here are a few of these walks. So think here that the vertical axis is discrete time, and each walker makes a binary decision at each step to either persist in its current direction, which preserves the color in this diagram, or switch direction, which means to change color. So if we look at these walks, for example, the first one, if we start out in red, well, it's just 3 persists in a row. We don't change direction. And this one, well, we persist, and then we switch, and then we switch again. Okay. So we can think of these things as instead of heads and tails, they're instructions to either persist or switch. So if we color their direction by, as we did in the drawing, red and blue, then we can think of a 2-component object. And so, you know, this guy is red, that guy is blue. And when you hit a switch, then you interchange between the two. And so then persistence then becomes this. It's just the identity matrix. And the switch just becomes sigma x. So what we want to do now is look at these walks, because we want to go towards the diffusion equation. So we look at this thing and say, well, okay, if we do an expansion of p plus s to the n, that's an expansion of sequential instructions. And so what we really want to do is figure out what this guy is. Okay, so the result will just calculate the probabilities of the walks partitioned into the final color. Now, to make contact with diffusion, what we want to do is we want to shrink the lattice size. So we want to make a lattice size small, and n is going to be large. But in order to look at it in the diffusion context, we're going to have to be a bit sly about counting. So because what we really want to do, we really want to count the number of paths between the starting point and the end point. So it looks something like this. So here are sort of 2D walks on a lattice, and you can see the walks, you know, if we go up here, that's persist, persist, persist. And if we're looking at going from the origin to some point on the x-axis up here, we can see we're going to be summing over a whole bunch of these binomial coefficients. So it's the binomial coefficients that we need to sum. And to avoid the tedious calculation, we're going to have to find a clever way to enumerate the paths. Now, matrix multiplication is going to take care of most of the counting for us, but we're going to need one more trick to track the displacement. So let's have a look at the trick. But before we do this, we have to introduce a disreputable character. This is the unit imaginary, and it's particularly disreputable in theoretical physics. As the physicists say, quantum mechanics is fun until somebody loses an eye. So we're going to have to take care to be very careful with the unit imaginary. We're going to introduce him and use him, but it's only temporarily. We're going to get rid of him in the end, and we're just going to use him because he's useful. So here's what we're going to do. We're going to take the persistence operator, which was the identity matrix, and say, okay, let's put these complex exponentials along the diagonal. Notice as delta x goes to 0, delta x is the lattice spacing in the x direction. As that goes to 0, we go back to the identity matrix. Here's the switch operator. This too goes back to sigma x when delta x goes to 0. And so we recover the original operators. Notice this other nice feature that p to the power n is just the same thing as p evaluated as k goes to nk. So what p does, products of p just counts the steps to the left and the right. So notice these exponentials. One is e to the minus ik delta x, and the one below is e to the plus ik delta x. So notice that 2 successive switches just return to the initial x coordinate, which makes sense from the paths. And just notice that when we do this expansion, P plus X, P plus S to the power n is a 2x2 matrix in which each element is a polynomial involving powers of this exponential factor. So let's just see what that looks like. Okay, so here's a particular case where we're saying let's take 4 steps, and we can look at these paths, and you know there's a bunch of them. So here's one, it goes all the way up here and then turns left, but then there's this one, and then there's this one. So there's 3 of these paths. Now, if we take the 4th power of P plus S and look at the 1, 1 element, so we're starting in red so you know, coming in here, we're coming in red. Here is what that expansion looks like. So why is this of interest? Why are we being clever when we do this? Well, we're being clever because what we really want to do is we want to get this 3, right? So the e to the minus 2I delta x k up here references the fact that we've gone 2 steps to the right. So it's really this thing that we want to get at. But there's and you know, if n was large, this would be a very, very large polynomial in powers of e to the I k delta x. Well, if we want to get at this coefficient, one way we can think of doing it is saying, well, take the entire polynomial, multiply it by e to the plus 2I k delta x. So this term now becomes the constant term, and now integrate over a period, which wipes out everything else because of the orthogonality of the trig functions making up the complex exponentials. So what we really want to do, we've made this transition to really Fourier space, and what we will want to do is then transform back. So here's what the task is. We want to take this, the limit as epsilon goes to 0 of persist plus switch normalized by this factor of 2 to the power of t over epsilon. So we're cutting down, we're partitioning time to be smaller and smaller. And the question arises as to, well, how should delta x, the lattice spacing in x, and epsilon vary in this? And this is actually determined by the statistics of random walks. The simplest expression of it from statistical mechanics is just to remember that the mean square end-to-end distance of an n-step random walk is of order n. So that if that's the way we take the limit, there's a self-similarity involved in going through the partitions and refining the lattice. So in that case, what we do is we say, okay, we're going to fix the ratio of delta x squared divided by epsilon, and set that to be a constant. So, and d is some positive constant. When we do that, we can take the limit, and what we find is, oh, well, we have this perhaps not terribly revealing result, except for the exponential. But remember, the square root of -1 is hidden in there. We're still in Fourier space. So let's see what that looks like when we go back via a Fourier transform. Well, what happens when we go back via the Fourier transform is we find this familiar looking guy here. Okay, and let's just notice that the scalar, that scalar amplitude, when you look, you see, oh, it satisfies this partial differential equation. So the point is, we've got to the diffusion equation, and we've always know exactly where we are, because we're always working within the probability model, and we know that we're in a sense just counting paths. So then now let's just appeal to authority. So we're going to ask Kronecker, and we're going to ask Cantor about that whole procedure. Now, Kronecker says, well, okay, the argument is all about number. The equation represents properties of large binomial coefficients. So that's Kronecker's claim. Cantor, on the other hand, said, well, look, you know, the equation itself has its own reality, and it's based on the continuum of real numbers. Okay, so as applied mathematicians, we can sort of look at these two perspectives, and to an applied mathematician, we can see, well, actually, Kronecker has a point. There's no physics in the equation itself, none. We only see physics, in a sense, when we see the similarity and dissimilarity between the random walks and Brownian motion. Right? When you see that, then you see, oh yes, I can go from looking at Brownian motion in fluids, and I can see where the diffusion equation comes from. But the actual derivation that we went through, in a sense, had nothing to do with that. It was simply counting. Cantor's point of view is to say, you know, stop fussing. You've got the partial differential equation. It's an entity in itself. Now, let's have a closer look. Kronecker would be riled by saying, forget the fussing. He'd say something like, the limit taken to produce the diffusion equation, it contains artifacts corresponding to the misuse of the concept of infinity. Okay, so what's he saying? He's saying, well, look, when you take this limit, rephrase that in terms of this. Delta x over epsilon is just the particle velocity. And when we look at this, look at the right-hand side. As delta x goes to 0, that goes to infinity, right? Nasty. So he's saying, well, look, there are other counterfactuals that correspond to this. One is a more modern statement, right? The fractal dimension of the particle paths is 2. They're in actual fact plane filling. And a rephrasing of this limit up here is that delta x, delta v is greater than or equal to some constant. I mean, we've seen that in quantum mechanics, and it's quite, we would call that the uncertainty principle, but clearly here there's a geometric analog of that. Other things that Kronecker would say are counterfactuals is the fact that the particle density causing the collisions must be infinite, and that, you know, tick and tock happen with infinite frequency. So Kronecker is not pleased with the whole result. Let's see what Cantor has to say. Well, of course, Cantor would be annoyed by all of this stuff being called counterfactuals, and he'd point out that, you know, the counterfactuals are contrary to what we would experience in the physical world, not the mathematical world. And the thing to remember is the two are not the same. So Cantor's response to Kronecker will probably say, look, you're thinking like a physicist. You're confusing the world of objects with the world of mathematics. So he might say something like, well, the diffusion equation is no more about diffusion than the Pythagorean theorem is about Pythagoras, right? So Cantor's response here is, look, the fractal dimension of the particle is 2. The uncertainty principle, the particle density causing collisions must be finite. These things that you're calling counterfactuals can in actual fact be removed anyway. See below. Okay, so let's see whether Cantor is right, and we can get rid of these things that look like velocity artifacts. So let's just recall we are generating walk sequences by sequences of these binary instructions. P represents persist. S represents the switch, right? So we're just saying we're going to trundle along in one direction, and then we're going to switch. And so this instruction set generates a list of sequential instructions. And as we refine the lattice, we want the expected particle speed to approach some fixed constant. So we're going to say that fixed constant is 1. And to do this, what we're going to do is we're going to rotate the square lattice by pi by 4, simply so it's easier to do the calculations. And we're going to refine the lattice. So when we do the refinement, delta x over delta t is always 1. Okay, and the things we need to patch in the derivation is we need the expected distance between direction changes should be finite, right? So tick and tock remain finite frequency, and the number of ticks should remain finite. So this is, in a sense, this is Cantor's ploy to say, okay, you object to all these things that you can call counterfactuals. Here's our patch. So here's a patch. So in terms of lattice refinement, here's the lattice turned on its edge. And so, for example, at this resolution, we can say, okay, here's a path, and the corners here are the ticks, are the switches, and the persistence is where the particle doesn't change direction. So notice in the left-hand side, at the coarse resolution, we have 3 switches. Well, here we are at the higher resolution. We still have the 3 switches, but we have a whole lot more persists, right? It's taking persistence through 4 steps to get to the first switch. Here, it was just through 2 steps here. So we want to incorporate that into the continuum limit. So how are we going to do that? Well, it's again through the probability. We're still going to employ the idea that the probability of the sample space is 1, and so P gets multiplied by 1 minus epsilon m, where m is some positive number, and S gets multiplied by epsilon m. So as epsilon gets smaller, the number of switches diminishes and the number of persists increases. And of course, so epsilon m has got to be less than 1. And so for t over epsilon is a large integer, what we'll be interested in is this guy here. So again, this is each one of those is an instruction, either persist or switch. Give them a probabilistic weight for either one and take that limit. So you can do that. And when you do that, you find, oh, this is what you get. Interesting form. And this is what I'm going to call the thermodynamic clock. It's a thermodynamic clock because it's really the way that time in nature seems to be measured according to how we interpret nature and how we interpret time as, in a sense, getting old. So another way of thinking of it is think of the isotope clock that one runs into. So the exponential decay is a way of, in a sense, measuring time. So there's that thermodynamic clock, and then there's also this sort of funny matrix that looks like a hyperbolic rotation, sort of. Okay, so let's now invoke this Fourier trick. We got the partition of states into 2 states. Let's try the Fourier trick, and same thing. So we're just going to say, replace the persistence by something that keeps track of persistence along the current direction, and then take that limit. Well, we can do that. Yes, out comes the thermodynamic clock. Notice when we do this, writing it in this way, we're beginning to see how the matrix algebra is actually trying to put things in terms of vectors. We can think of sigma z and sigma x as being vectors, and so this is rather a compact statement of what happens. And it turns out that when you look at f and you say, well, we're still in the Fourier domain, we've got to get rid of that underlying square root of -1 by going back to the spatial domain, we find we end up with this as the partial differential equation. And that is a form of the telegraph equations. So, okay, let's see what Kronecker has to say about that. Well, Kronecker is going to stick to his guns, right? He says, look, this argument is still about a number. He's smarting about the Cantor's treatment of what he had to say. He points out that, look, the fractal dimension and the uncertainty principle are not removed by this procedure. Both features are in actual fact aspects of binomial coefficients as they relate to scale, which was shown in the previous thing. The counterfactual aspect of fractals and the uncertainty principle is the unwarranted extension to arbitrarily small scales. So he's being specific, really, about what he's objecting to. And he sort of backs that up by saying what we already know, that the solutions of the Telegraph equations, they look like the solutions of the diffusion equation on scales that are large compared to 1 upon m, precisely because we are still describing sums of binomial coefficients. So his complaint, in a nutshell, is the formulation as a PDE just hides these facts. All right, so Kronecker sticks to his guns. It's not going to convince Cantor, though. So Cantor, at this point, says, yes, the continuum limit is a convenience, but the language after the continuum limit is consistent. As Kronecker says, it represents features of numbers over a large range of scale, and it constitutes a view of properties of binomial coefficients in its own right. And it is difficult to get this simple view without the continuum limit. And, you know, regardless of your hesitation to use the idea of infinities, the utility of the partial differential equation simply is undeniable. And, well, of course, he's correct in that. So let's just compare these two views. Here are the two equations we've got. The diffusion equation, the Telegraph equations, they're bog standard in statistical mechanics. Kronecker says, well, look, the equations are approximate expressions about features of sums of binomial coefficients. So he regards the continuum as an approximation. Their invocation are example of Bishop Berkeley's rather nice ghosts of departed quantities, in which the departed quantities are the actual reasons the ghosts are there. Right, so he's saying, look, this is all about how you got there, and it's about counting, and the end result dismisses that. You can't see where you got it from. Cantor, on the other hand, dismisses this and says, well, look, the PDEs have meaning in their own right. The departed quantities are the details that would otherwise cloud the simplicity that the equations represent. So at this point, they both men have, you know, their points of view. You can understand both of them. They're both sticking to a perspective on the whole issue. So this last statement by Cantor is so far his really only unguarded statement, if he would ever make such a thing, right? The departed quantities can, in any case, be recovered by examination of the arguments used to obtain the PDE in the first place. Well, that's true, because we just did that. We went through the argument to get the PDEs. But of course, this is prior to quantum mechanics. And, you know, with the advent of Schrödinger's equation and Dirac equation, that turns out to be not true. We've had these guys for nearly 100 years, and there's no joy in getting it directly from the perspective of probability theory. So let's just have one more look at the Telegraph equations. So all we're going to do with the Telegraph equations is we're going to have a closer look and retain a bit more information. So we're going to retain more information by, instead of looking at 2 steps, we're going to look at 4. So here's what P is going to look like. So this is moving to the right, moving to the left, moving to the right, moving to the left. So our switch matrix, well, this is, you know, 4 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4. We're simply switching back and forth, left and right. And so the switch matrix, all it does is it moves us down. 1 goes to 2, and 2 goes to 3, and so on. But this time, before we take the limit, we're going to change variables in a suggestive way. Right? If we say U is a column vector of the probabilities in the 4 states, we look at a column vector Z that adds 1 and 3. Remember, state 1 and 3 are both right moving. state 2 and 4 are both left moving, so the two z's, first z's, will just reproduce what we've already just calculated. These guys here, the u1 minus u3 and u2 minus u4, are not probabilities at all, right? So the first ones are probabilities. The last two are differences. So we can then just simply do the change of variables. And the interesting thing that happens is that when we change the variables, the configuration generator becomes block diagonal in form. It's two 2x2s. The upper block containing the probabilities gives exactly the same two-component equation as before. So when we take that limit, the upper two, there's the old thermodynamic clock. Here is this expression of f in terms of the hyperbolic functions. But notice what happens to the lower two. This is a little bit of a surprise. We get the thermodynamic clock, but the hyperbolic goes over to trig functions, and EP gives us this rather familiar looking, what we would in physics call the energy relation. Oh, and look here. This guy, well, this is just Lew's clock, right? It's the I guess I sigma y. Its square is minus the identity matrix. And so when we look at this thing, we can ask, well, okay, well, what does Z satisfy? Well, just removing the thermodynamic clock, this guy satisfies the Dirac equation in a two-dimensional spacetime. Okay, so we looked at that. The hyperbolic functions have been replaced by the trig functions. The energy momentum relations are the usual form. The switch matrix has changed from sigma x to what amounts to I sigma y. The process that this result discovers, so the process that this result discovers is sitting underneath the Telegraph equation. It lives completely in the classical world, but it's hard to see. You have to look closely. And as a feature of a stochastic process, ZPT functions as an autocorrelation function. So we know what it is in the classical world. So let's have a quick look at something that is well known. We have these equations, the classical equations. These are all equations that, for example, from a physics perspective, you say, well, okay, we understand those equations via kinetic theory. They're all, in a sense, straightforward. We looked at them from the point of view of probability theory. We know the theory that underlies them, and we've seen today that we've looked at this guy and we've looked at this guy, and both of them are expressions of the probability model. So we don't need to go to physics at all. They're just, as Kronecker would say, they're manifestations of the binomial choice coefficients, which are a feature of counting. They live in the discrete world. But we just saw that if we looked a little bit closer, we've got this guy here. So that's really the Klein coordinate equation, and that's usually thought to be completely distinct, right? There's a barrier between these two, and usually the way you go from one to the other is through a formal analytic continuation, which just says, okay, pick the right constant and multiply it by I, and you now have a new equation. And over here, the object being looked at is this thing called the wave function, and it is outside the classical domain, except in the one case that we've seen where we now know what that is in terms of probability theory. So again, let's ask our two experts to comment on this. So Kronecker, again, he sticks to his guns and says, look, everything in the classical column gives an approximation to the features of sums of large binomial coefficients. The probability axioms simply express these features as ratios of large numbers. The Dirac equation is included in this view. Here, there are differences of binomial coefficients involved, And note we had to see the whole argument, continuum limit included, to find the Dirac equation, right? It didn't just present itself to us immediately. Cantor, of course, sticks to his guns too. Yes, but the limiting process provides a symbolic picture of what is going on. Expressing these particular results in the discrete world is much more difficult, and you would be hard-pressed to see the forest for the trees without the resulting PDEs that require real numbers. So, okay, there's no real resolution between Kronecker and Cantor on this, and as applied mathematicians, we can see the two visions. One is that counting is all about counting. The other is saying, look, take magnitude, consider real numbers as being mathematical objects that we can understand, and it's all simpler. Now, of course, those two quotes aren't quotes, they're manufactured. Here's an actual quote from, an important person. So this is Dirac saying, this result, the Dirac equation, is too beautiful to be false. It is more important to have beauty in one's equations than to have them fit experiment. Now, I have to say, this isn't just narcissism on Dirac's, account. The whole idea about beauty in mathematics and physics, in some ways, he changed the whole idea of theoretical physics. He's not alone in looking at equations by how, in a sense, beautiful they are, right? So here's Frank Wilczek, a giant and a thoughtful giant of modern theoretical physics. Of all the equations in physics, perhaps the most magical is the Dirac equation. It is the most freely invented, the least conditioned by experiment, the one with the strangest and most startling consequences. So I think he's in accord with, modern theoretical physics. John Slater, back in 1975, the previous generations of physicists, of course, who saw the transition gradually going from applied math-oriented physics to modern theoretical physics, there always was this idea of a rabbit out of a hat for not only not only the Dirac equation, but quantum mechanics in general. And I have to say, my favorite quote, which has a typically English sense of humor attached to it, is by Penrose, who says, quantum theory has indeed two powerful bodies of fact in its favor, and only one thing against it. First in its favor are all the marvelous agreements that the theory has had with every experimental result to date. Second, and to me almost as important, it is a theory of astonishing and profound mathematical beauty. One thing that can be said against it is it makes absolutely no sense. So, I think that sort of sums up the Dirac equation, in some ways how it's seen. So where are we? Okay, so we found these two classical PDEs by following binary choice and probability theory through what seem like sensible continuum limits. We have done this as applied mathematicians. There are complaints, right? There are complaints from Kronecker about the continuum limits. He would say that diffusion and telegraph equations reflect aspects of sums of binomial coefficients, partitions into groups of two, distinguished by 0 and 1 mod 2. He would point out that the Dirac equation reflected aspects of differences of the binomial coefficients, partitioned into 4 groups, right? So in terms of what we've gone through, my guess is most theoretical physicists would accept the derivation of the Dirac equation with comment that, by its derivation, it violates the context in which the equation appears in theoretical physics. It's not a threat to theoretical physics because it is just about number. It's just about binomial coefficients, and it appears in the mathematical spectrum without having to be attached to anything in particular. We can attach it to probability, but if we do so, we have the thermodynamic clock attached to it, and so it's harmless. But one thing that we should notice is the appearance of the Dirac equation in this context. It reminds us that the existence of a manifestation of large numbers gives it, in a sense, a reality that is likely as strong or stronger than the diffusion or telegraph equations. It's just that the way we've come through it, we can't see it. We can't see what the relevance is. So next time, if there is a next time, in the arguments that we've gone through, we've assumed the analogs of space and time were independent. It was central to our argument, but we didn't say much about it. And so what we really have to do is find out what happens to the arguments when the Lorentz transformation comes into play. Okay, so spoiler alert, this is what we're going to do. We'll see that the Lorentz transformation, it breaks the probability, the probabilistic context of the argument through the magnitude aspect of probability and not the number, right? So going back to those primitive binomial distribution that has the binomial coefficients and then the probabilities, which are magnitude. It's the probability of the sample space that breaks when you start looking at a time dilation. And it turns out that in two ways of taking limit. One way leads to the conventional special relativity. The other leads directly to the Dirac equation with marked world lines in an inner scale. So the rather charming thing about this is that when you look at the derivation from the discrete picture, you get the detailed information. You know what the wave functions are, what their function is, what they're doing. And in actual fact, what they do is they bring a time dilation in a sense to the view of the partial differential equation. And we'll see that we need the Clifford algebra, or in its absence, the unit imaginary to do that. Okay, so that's next time. If anyone is sort of interested in following some details, just a couple of references. One is on the archive. It's this was basically an article that was to address statistical mechanics, and it provides a bit more of the details. And where a lot of this started was the Feynman chessboard model, and probably the best paper for that is by Blue Kaufman. And you can find it in the physics letter, so probably just asking for it. So thank you all for listening. And if there are any questions.